Hi there, Physics 131. A little bit of a shorter pre-class reading video today because we're finishing off Chapter 9 today, and there's really only one section left. Section 9.5, Rotational Kinetic Energy. So as I mentioned before, we did rotational momentum, and now we're finishing off with rotational energy. So remember, kinetic energy is 1/2 mv squared. Well, you can imagine that the rotational kinetic energy is 1/2 I omega squared. And she actually derives that for a particle that's moving at some linear speed. You can pretty quickly show that it's with mr squared as being the rotational inertia of a particular particle. That's how you get this equation. So there's an example here of doing some work. You apply a 5 Newton force to this solid sphere and pull it over some distance, okay? Then you can use this energy equation. Initial energy plus the work equals the final energy. And in case of kinetic K, use 1/2 I omega squared. So there's problems to be solved that way. Here's another one where you have a round object that's rolling down a hill. The idea here is that when you're rolling without slipping, you have a surface which is static, and so the static friction force, which causes it to roll as it goes down, does zero work. So what's happening is that there's conservation of energy. If you start from rest, because you release the object from rest, it has 0 translational kinetic energy plus 0 rotational kinetic energy. But you also add the gravitational potential energy mgy, that's the UG. So it starts with some mgy, some gravitational potential energy. When it gets to the bottom of the slope, then y goes to 0, so the mgy is 0. But you now have 2 kinetic energies. You have the translational kinetic energy, 1/2 mv squared, plus, because it's rolling without slipping, it's rotating, you have the rotational kinetic energy, 1/2 I omega squared. So the equation you end up with is mgy initial, and then plus all those zeros, is equal to 1/2, I guess the mgy final, which is 0, plus 1/2 mv squared, where v is v final, plus 1/2 I omega squared, where omega is omega final. So there's a lot of equations there. We'll do a demonstration of that in class. It talks about flywheels for storing and providing energy. You can imagine inside a car or in a power plant or something, a very rapidly spinning massive disk. It will contain energy. And so it's one way of storing energy. And that's pretty much it. I guess there's section 9.6 we're going to skip in this class, so don't worry about that. So really at this point you're done your chapter 9 reading. The summary here is good to go over. We have rotational kinematics with theta, omega, and alpha as your new rotational I guess position, velocity, and acceleration. We have rotational inertia, which for a particle is mr squared, but then when you have different shaped objects, you will have some fraction out there in front of the object of the equation. We have Newton's second law for rotation, which is alpha is 1 over the rotational inertia times the sum of the torques. Rotational momentum, L, is equal to I times omega. And then there's conservation of angular momentum if there's no, or rotational momentum if there's no torques. And then there's rotational kinetic energy, 1/2 I omega squared today. And so that's the summary. And then next time we'll start in on chapter 10. Bye for now.